big influence on the distance. When we add a mass of 25 grams more, our distance will lower of about 4 meters. And this is a very big difference here. We have done this measurement with our car and we put additional masses on it. Now to the influence of the radius. As I said, this is a very interesting parameter. You see here the distance traveled in dependence on the radius of the nozzle. There's a critical radius for about 1.1 millimeters, where the propulsion force equals the friction forces. For a higher radius, the distance will increase very fast until it reaches a limit for very high radius. And this is theoretically, and as you can see, it is also practically proved by experiment. So here you can see a video of my final car. Now the air goes out of the balloon, the car accelerates, now the air is completely out of the balloon, but because of inertia the car moves forward, and now because there are friction forces, as I mentioned, the car decelerates and stops. Now, yeah. And to come to my conclusion, here you see one time more my car I used, my final car, and here we have the CDs as wheels because they have a very small rolling friction factor, they have a small moment of inertia and a very small cross section which leads to a small air resistance. Then we use this long balloon here because it has also a small cross section for a small air resistance, and it has a very high energy density in it because of the high air pressure. Here at the end you see our nozzle, which has a comparatively big radius, so that the, as I mentioned, the distance will reach saturation for high distances. So our final efficiency of the car we reached was about 1.2 meters per joule. Thank you for your attention.
Thank you. Time for questions.
Thank you for your great presentation. So first of all, according to your definition of efficiency, the point which the efficiency is maximized is just synchronized with the point where the efficiency is maximized. Is that correct according to your presentation?
Yeah, I've maximized the efficiency, or what you want?
Yes, but then for the car to travel a longer distance, it should experience a greater maximum velocity, and it means that it will experience a greater air drag and also the rolling friction, so that it experiences a greater energy loss. Don't you think that should be taken into account?
Yeah, I have taken it into account.
Yes. Also, according to your definition, your formulation of rolling friction, it was not proportional to the velocity of the car. However, according to the car's contact area of rolling friction, it should be proportional to the velocity. So, don't you think your term for rolling friction should include a velocity term as well?
Normally, the definition of rolling friction is not proportional to the velocity. It's not dependent on the velocity. But you have the air resistance.
Talk about it in the discussion then. Have you experimented with different nozzle angle, the direction of the thrust force acting on the car?
You mean on an inclined plane, the car?
Yeah, this is a horizontal plane and this is the nozzle angle. Have you
okay. Yeah, I've made experiments and also theory, and the drag force will decrease with the cosine of the angle alpha, and so the efficiency will be lower in this case.
Yes, thank you. Then you mentioned about the turbulence, but then don't you think as the nozzle diameter increases, the flow rate through the nozzle will increase as well, so that it will cause a turbulence, so that there would be a certain tick point in your data for the nozzle radius. Don't you think so?
Yeah, for bigger radius, the correction factor from the Darcy-Weisbach equation changes, but we haven't considered as big radius.
Okay, you can start.
So hello ladies and gentlemen, this is Song-Yeon Yam from Republic of Korea, and I'm going to present on reputation for the problem number 5, car. So first of all, the presentation overview. So first of all, the Germany team defined the efficiency as distance traveled over energy, and after that they explained about the masses to reduce the friction term, and they experimented with the Reynolds number to confirm about the turbulent flow. And after that, they drew a free body diagram. And after that, they explained about how would they measure the volume energy calculation. And they the volume pressure change, but we thought that it needed some improvements. And also in the experiment part, they measured the rolling friction term, but we also thought that it needed some corrections. And also in the experiment, they experimented with mass and also the nozzle radius, and they concluded that their maximum efficiency was 1.2 meter per joule. And then next I will explain about some of the fallacies on the presentation. So first of all, their definition of efficiency was quite controversial, so that we thought we could have some discussion on it. And also their network equation, we also thought that they needed some correction, since as the angle of the nozzle changes, the angle at which the thrust force acts will change also, and it may also decrease the friction acting on it by decreasing the lower force. And also on the free body diagram, the friction there, according to their explanation, it only included the rolling friction term, but it did not include the static friction term. But however, considering the fact that rolling friction only acts to decrease the angular velocity, I think it needs some corrections. And also, on the rolling friction term, according to the Hurst contact theory, the rolling friction value is proportional to the velocity, but they did not include that in their explanations. And also considering about the turbulence, the airflow rate would change according to different nozzle radius and also the nozzle length. However, they included the explanation about the turbulence. However, they did not experiment with different nozzle radius, neither the different nozzle lengths. And also on the input energy calculation, the range for the integrals was quite strange, since it is to integral up, the upper boundary was infinity. And also some of the important parameter would be the nozzle angle, but they did not include that in their theory. And also they did not deviate theoretical expectation on their value of maximum efficiency, so we thought that it needed some improvements. So next on this experiment part. So they did not clarify whether they measured the pressure of the balloon when they expanded it, or when they measured the pressure of the balloon when it contracted. And also, their pressure sensor was quite far from the balloon itself, and it meant that some of the frictional losses will occur as the air flows from the balloon and to the pressure sensor. And also, they did not mention how did they control the balloon, and also they mentioned about the airflow speed, but they did not mention about how did they got the volume. And also, their car model did not have the nozzle stabilizer, so that the nozzle could have some instability, so that there is a change in nozzle angle and also the direction of the propulsion. And also the distance measurements, they did not use a rail, so car would go in a very random direction, so that their experimental method in the distance measurement should have been clarified. And also they lacked some variables like nozzle angle and the wheel size. So move on to some of the discussion topics. So first of all, I would like to ask the reporter team that usually when we define efficiency, we define it as a input energy over output energy, so that it is kind of a dimensionless value. However, do you think it is okay to define the distance as the input energy part?
Yeah, I have defined my efficiency like this because, first of all, real cars, as I said, have also a definition of efficiency, which is defined as cruising range per fuel tank. So this fuel tank, which means also energy. So this is, in this case, the same. And then, additionally, the output energy, what do you define as output energy here, in this case? What do you define your efficiency as output energy?
Output energy, we think that it should be something related to the kinetic energy of the car. But however, I would like to develop more on your definition of efficiency.
Okay.
So let's say the car travels over, let's say to maximize the efficiency, we have to minimize the frictional losses. However, if the car travels over a longer distance, it means that it will have a greater frictional losses due to the air drag and also the friction with the floor. So it means that if the car travels over a greater distance, it will also experience a greater frictional losses. So do you think that, considering that fact, do you think your efficiency definition is quite validated?
Yes, of course. When the car travels a longer distance, it must not be that the velocity is also higher.
And I would like to ask you, so when measuring the coefficient for the air resistance, like approximated that it is a constant value.
Yes.
However, like as car moves, the balloon will exude some air so that the shape of the balloon will change, and that means that the coefficient of air resistance should have been changed as well.
Yes, that's right. But I have made very much measurements of the car when the balloon is blown up and a bit blown up, and I took all values and made the average out of it.
Thank you. Then let's move on to the nozzle angle part. So let me show you some kind of free body diagram for the car. When we look at this diagram, so we can say that the car will receive the nozzle angle is tilted, and the car will receive a horizontal propulsion force and also a vertical upward force. And it will decrease the value of lower force so that it will receive a less friction. So don't you think the nozzle angle can be a very influential parameter to increase the efficiency of the car?
It can be it can have an influence, but I made also some experiments with this, and I measured that it has no effect. So we have almost the same value of the drag force for 0 to 20 degrees for this angle, and for higher angles we have a smaller force.
So do you have the experimental data on your? Can you show us your experimental data on the nozzle angle? Do you have it in your?
No, sorry, I haven't it here.
Okay, so it would have been better if you included your data on the nozzle angle for your presentation. So now let's move on to the next topic for the turbulence. So as you have mentioned in the initial point of your presentation, turbulence is a very important concept to measure this problem. However, according to this equation, the flow rate will be dependent on the nozzle radius and also the nozzle length. So it means that as the nozzle radius increases and the nozzle length decreases, there will be a turbulence generated in the nozzle so that it will decrease the propulsion force.
Yes, the problem of this equation is that it's only valid for laminar flows, and we have definitely a turbulent flow in our nozzle. And
No, it's
So do you
also
mean
no,
that you have
pravica
turbulent
doesn't
flow
have
for
pace.
even the small radius nozzle, like the very small nozzle radius?
yes, even for the critical radius for 1.1 millimeters, we have even there a turbulent flow.
How did you measure the airflow velocity?
I have, can I go into my presentation? Can I go into my presentation? And
Sure,
yeah.
during the discussion, it's your right to have using the projector. So please avoid and detach your presentation and go for the presentation of the report.
So I've shown you the measurement of the Reynolds plot at the beginning, and here you see this black measurement points, and out of this you can easily compute the volume flow, and as the velocity of the air times the cross section of the nozzles, the volume flow, you can easily calculate out of this our velocity of the expelled air.
So which measurement did you use to get the value of this?
Yes, I used the measurement with the video analysis I've shown you.
Okay, thank you. So,
This measurement.
however, considering also the nozzle length, so have you experimented with the different nozzle lengths?
Yeah, so I've here I've first included in my formula my nozzle length, and so it's clear that when you have a greater nozzle length, the pressure losses will be greater also, and so it's I don't make experiments here because it's obvious that for a small length the efficiency will be greater.
However, this is a good point that you consider the frictional loss. However, as the nozzle length increases, the airflow will stabilize so that the turbulence inside the nozzle will be decreased, and it will cause a laminar flow. And so, if considering the fact that turbulence will hinder the airflow from the nozzle, don't you think if we increase the nozzle length, it can also be some positive effect for the efficiency as well?
I don't think so, because